Hi guys, this video goes with the note sheet that says water potential. I'm hoping that through this you'd be able to do those calculations for our diffusion and osmosis lab that we did, the other day, like the 4th, whatever day that was. Yeah, Wednesday, I believe. So at the very, very back, after you do all the tables and the graphs, you actually have some questions. Most of them are conclusion and analysis questions, and a few of them require you to know how to calculate water potential and solute potential. So hopefully this video will give you the information you need in order to do that. So we're going to step through it. Here we go. So you're used to hearing about osmosis, and you're used to the definition of osmosis being the movement of water from a region of high concentration to a region of low concentration. And if we really want to get fancy, sometimes we throw in the words through a semi-permeable membrane, for example, the cell membrane or dialysis tubing, just to make it snazzy. But there is actual math, an actual reason as to why water is going to move from high to low. It doesn't just do so because it feels like doing that. The reason water always moves from where you have a lot of it to where you have a little bit is because of something called water potential. And water potential can be defined as many things, but the two main ways that I like to think about it is it's the force responsible for the movement of water in the system, and it's also the potential energy that water has to move. Okay, so the ability of energy available for movement. That's the main reason why water is moving from high to low. So it has a very weird sign, which is called psi. Okay, so this is the symbol psi, and psi comes from the Greek alphabet. So one of the ways that I always remember it, I don't know if you know this about me, but I am a huge Greek mythology enthusiast. Like, I just love stories and books about the ancient Greek gods like Poseidon and Hades and Zeus and all of that. But the way I remember Psi is because there was a Greek god of the ocean, or water if you want to think of it, called Poseidon, and this symbol is named Psi, and his symbol of authority or rulership or whatever was the trident, which Psi kind of looks like. So Poseidon, Greek god of water. Psi is the symbol for water potential. It looks like a trident, which is what the Greek god of water carried. Hopefully this helps you. Psi can be measured in two main ways. We can talk about psi in terms of bars, or we could talk about psi in terms of megapascals. For your AP test, more than likely you will see bars, but just be aware that it can be both. So one of the reasons that water potential is sometimes a hard concept is because it tends to be an abstract concept. So we have to really break it down and think about it from a logical perspective. So when water has things diluted in it, when there are solutes in water, the water molecules actually surround those solutes if they're dissolvable, preventing them from going back together. But that also ties those water molecules up. Like they're now committed to being around this chlorine atom or this sodium atom. So another way to think of water potential is that it's the measure of, or the measurement of, the free energy of water. And you tend to have less free energy from water if it has things dissolved in it. So the more solutes you have in a solution, the less free energy that water has, the least likely it is for it to move. Okay, so another way to think of that is if your water is not going to be doing a whole lot of movement, it has low water potential. It has a very small amount of energy available for movement. It is hypertonic. It's not going to move. The water from someplace else is going to move into it. Okay, so water potential is made up of two components. The first one being solute potential, which is sometimes called osmotic potential, and its little symbol is the same psi, but with a little s. And your solute potential is going to depend on or be determined by your solute concentration. How much stuff are you dissolving in your water? So in other words, what is the molarity of the solution that you are working with? The other component is pressure potential. And your pressure potential is going to be literally like a physical pressure, a physical force, or pushing or pulling, however you want to think of it, on the membranes or walls as water moves into a cell, for example, or out of a cell. Pressure potential can be both or either positive or negative, whereas solute potential is always negative. So when it comes to water potential, we always use pure water as our absolute value, okay? It's kind of like our Zen, if you want to think of it from that perspective. So your water potential for pure water is given the value of 0. And it's because pure water has the highest or the most water molecules and the least amount of solute particles. Okay, so there's not anything really dissolved in pure water. So thus it has the highest water potential. Okay, which means that everything else, every other kind of solution has some solute in it, even if it's not a whole lot, it's still there, it still exists. So it means that every other kind of solution has to be lower than 0. So it means that every other solution has a solute potential that is negative. So adding solute is going to decrease your water potential. It's going to decrease the likelihood or the energy available for water to move. The more solute that you have present in a solution, the more negative that value is going to be, the more negative the solution becomes in terms of the amount of solute. So solute potential is always going to be a negative number as long as your solution isn't pure water. If your solution is pure water, then the solute potential is 0. But if your solution is not pure water, then it's going to be some negative number. You can think of solute potential as a pulling force. It pulls water towards it, okay? So that's one of the reasons that it's always going to be negative. You just have a lot of solute dissolved in that liquid. Solute potential, again, is a pulling force, pulling water towards it. Another way to think of this is your hypertonic solutions are going to have negative solute potentials because they have so many bits and pieces and particles dissolved in them. Okay, so I feel like pressure potential gets very little love, so let's talk about pressure potential for a little bit. Now, while solute potential is always a pull, meaning it's always going to be negative, pressure potential can either be a push, so it could be a positive value, or it could be a pull, a negative value. Pressure potential doesn't often play a role. There are 3 main ways or 3 key areas that you will see pressure potential involved, and it's normally if the cell involved has a cell wall, so it's some kind of plant cell, or some cell that has a cell wall, or we're talking about transpirational pull, where water is evaporating out of the leaves of a tree, and that's causing water molecules to move up the tree. We can also see pressure potential playing a role if your system is a closed system. So meaning it has like walls on all sides of it. So for example, a closed system would be, a container with a lid. Like your reaction is happening inside of a container with a lid. Okay, so really quick, let's look at the formula for water potential. So water potential, which again is psi, is equal to your solute potential plus your pressure potential. It's a very simple formula. This is not one that you have to memorize because it is provided for you on the formula sheet that you will use on your AP test. Okay, so let's go back to talking about water and its movement again for just a little bit. So again, we're used to the concept of osmosis where water moves from high concentration to low concentration. But now we need to throw in some of that new terminology that we've just learned. So I need you to start thinking of water movement in terms of water potential. So really what happens is water moves from areas of higher water potential to areas of lower water potential. So water moves from where it's less negative to where it's more negative, wherever it's more concentrated. The way I remember this is I think of a waterfall and the fact that water is always falling down from high to low, so it moves from high to low water potential. So water is always going to fall from high to low, high to low, high to low, until the water potential inside of your cell is equal to the water potential on the outside of your cell. That's the only time you're not going to have water movement. And even if I shouldn't say that you're not going to have water movement. For some cells, it means that you're moving equal amounts of water. For others, it means that you're not moving any at all. It depends on the presence of that cell wall or not. But that's the only time when you're not going to have that high to low movement is when you have the same water potential on the inside of your cell as you have on the outside of your cell. All right, so let's do a quick check-in. This is not making any sense at all. These are the things that I really need you to understand. You need to look at that equation and just realize that water potential is made up of solute potential and pressure potential. You need to know that the water potential of pure water is 0, and that you need to know that water moves from areas of high water potential to areas of low water potential, meaning that they're always moving towards the region that is more negative. If nothing else made sense, these 3 things are what you need to hold on to, and that's what needs to stick with you. So please put these under the main points or main goals or whatever section of the notes. So what happens when a potato cell is put in pure water? Sorry guys, Ms. Malin was calling. So, like I was saying, what happens when a potato cell is placed in pure water? Well, water is going to move either into or out of the cell until the water potential of the cell itself is equal to the water potential of the solution that the cell is in. Now, pressure potential is going to increase in order to balance out your solute potential. We're always trying to achieve that 0, always trying to get closer and closer to the water potential of pure water. Eventually, we're going to get to a point where no net movement of water is taking place. We're not losing water or we're not gaining water. So remember, when we get to the point where we are not losing or gaining water, it means that the water potential inside of the cell is the exact same as the water potential on the outside of the cell. So how can we determine the water potential of potato cells? Well, we pretty much do the lab that we worked on Wednesday. We would take potato cells, place them in different molarities of sucrose solutions, and then when enough solute has been added outside of the potato cells, we're going to get to the point where they're not going to move. There'll be no net movement of water. And when that happens, you've achieved the molarity of the potato cell. The molarity on the inside is going to be the exact same as the molarity on the outside. Okay, so yes, you understand that, but how do we see this? How would we showcase this? Well, this is where your graphs come into play. And sometimes you might see questions represented on the AP Biology test in this manner. So you would take your information, you would graph the results as the percent change in weight of your potato cells based on their different molarity solutions. And wherever that line that you will create from your data crosses the x-axis, that represents where there is no gain or loss of water, and that is going to be the molarity of your potato cell. Okay, so let's look at some simple water potential calculations. This first one says a cell has a solute potential of negative 23 bars and a pressure potential of 2 bars because it is in a closed beaker. What is the water potential? So the first thing you're going to want to do is start with your formula that says that water potential is equal to solute potential plus pressure potential. And then we're going to substitute in our values. Now, sometimes on the AP test or in labs or in class, you might be asked to calculate just plain old solute potential, or sometimes they'll ask you to calculate water potential. They'll give you enough information to calculate solute potential, but they won't actually give you the value of solute potential. So you need to not just know how to calculate water potential, you also need to know how to calculate solute potential. And that is a completely different equation. Your solute potential equation says that it will be this one right here. It says that you're going to find solute potential by taking negative I times C times R times T. So let's talk about what all of these things mean. That I stands for the ionization constant. And your ionization constant is going to depend on if your solute dissociates, or breaks apart in water. So most often it has a value of either 1 or 2. We use the value of 1 if it's something that does not break apart, like sucrose. Sorry, keep hitting this button. Okay, but if it's something that does break apart, like salt, for example, we use the value of 2 because you're literally getting sodium ions and chlorine ions. Okay, and those are the most common examples or ones that you will see in the question. C is the molar concentration of your sucrose, or whatever that solute tends to be. R is going to be your pressure constant, which we always use as 0.0831 liters per bars per moles per Kelvin. This value you do not need to memorize because it is going to be on your formula chart. And then T would be temperature, but it's going to be the temperature in Kelvin, so you're going to have to do some conversion. It's a very simple conversion. You will take whatever the temperature is that they gave you in degrees Celsius, and to that number you will add 273, and then you've converted into Kelvin. So these have a lot of units, but most of the units, if not all of the units, cancel out to leave you with bars. And that's adequate because you're finding solute potential, and solute potential is normally measured in bars. So again, this is the formula for finding solute potential. These are what all those variables stand for. All right, so let's work a problem. So it says, so what is the solute potential of a 10 molar solution of sucrose at 22 degrees Celsius? So again, you would be utilizing that formula that says it's negative I times C times R times T. Don't forget the entire thing is going to be negative because we are calculating solute potential, and solute potential numbers are always negative. So our ionization constant in this case is going to be 1 because we are working with sucrose, and sucrose does not dissociate. Sorry, I keep wanting to say deionize, but it doesn't dissociate in water. So our ionization constant is 1. R is our constant that never changes, so that's going to be your 0.0831. You get that on your formula chart. T we know is going to be our temperature in Kelvin. They told us that we're working with 22 degrees Celsius, which means that we're going to be adding that 22 to 273, which should give us a final number of 295. So then it's just about multiplying all of these. 1 times 10 times 0.0831 times 295, keeping in mind that it's going to be negative. So your answer would be negative 245.2 bars. How do you know how many sig figs that you need to keep it to? Let's look at the question. Right here, we go to 1, so here we go to 1 as well. 1 sig fig after the decimal, that is. Okay, so from that last question, you would have just calculated solute potential. So then how do you find water potential? Well, once you have your solute potential, it's just a matter of plugging that value in to your water potential formula, figuring out if your pressure potential is going to be 0 or if they actually gave you a value for pressure potential, adding the two values together, and the answer would be your water potential. But of course, we're not just going to leave it like that. We're going to do a practice question on this next slide coming up. So the question says, calculate the water potential of a solution of 0.15 molar sucrose in a beaker at 20 degrees Celsius. And it goes on to say in an open beaker, the pressure potential is 0. So we are using the formula that says our solute potential is equal to, is equal to negative ICRT. So in this case, our I is going to be 1 because we are working with sucrose, and sucrose does not break apart in water. Our constant, not constant, but our concentration is based on what they tell us in our problem. So that is going to be 0.15 molar. Then our pressure constant is going to be 0.0831. And our temperature is going to be 20 plus 273 to give you 293 Kelvin. All right, so that's going to be equal to negative 3.65, and that answer is going to be in bars because we're calculating solute potential. So, but this is not what the question asks. The question wants us to find water potential. So now we have to go back to our original formula that says water potential is equal to solute potential plus pressure potential. Well, solute potential is this negative 3.65 bars. Pressure potential is 0 because that's what they've told us. So our water potential is negative 3.65 bars. Okay, and this would be your final answer. So this is one of those two-step questions where you're going to first have to calculate your solute potential and then plug that into your water potential formula. Now we could completely change all of this if we just made our solution out of salt instead of out of sugar. So I'm going to add in a slide real quick and show you what that would look like. All right, so it's the exact same problem as before. We're still working with 15 molar solution, but this time it's made out of salt, not out of sucrose. Our pressure potential is still 0, and our temperature is still 20 degrees Celsius. We are still finding water potential, but we're going to have to start with solute potential first. So our solute potential is going to be equal to, solute potential, not pressure, is going to be equal to negative ICRT. This time our I is going to be 2. Remember that I stands for ionization constant, and it's dependent on whether our solute will break apart in water or not. Sodium chloride does break apart in solution, so it's going to have a value of 2 and not 1. Our molarity is going to stay the same because it's still 0.15 molar. Our constant is going to stay the same. It's still going to be 0.0831. And our temperature is still going to be 293 Kelvin. Okay, but this time, because of that added ionization factor of 2 and not of 1, our solute potential is now going to be 7.30. But again, and this isn't in bars, again we are finding water potential ultimately, so we have to plug that into our original formula that says water potential is equal to solute potential plus pressure potential. And we know that our solute potential is this negative 7.3 that we've just calculated. Our pressure potential is still 0, so overall our water potential is going to be negative 7.3 bars. And again, that's your final answer. Okay, so hope this was helpful, not too stressful. If you have questions or you're still unclear about certain things, feel free to come into tutoring or to see me or shoot me a message. See you guys soon. Bye.